This presentation covers REPL-driven development in JavaScript. I'm going to start with some background, including what it is and what led me to it. Then I'm going to demonstrate it for you using a tool I made. And finally, I'm going to share what I've learned using it as my main workflow in my day job for the last 4 years. REPL-driven development grew up around an Emacs key binding that evaluates the bit of code near your cursor and displays the resulting value. To do REPL-driven development, you write or change some code, evaluate it, compare the result with your expectations, and repeat. The integration between text editor and REPL means that you never have to copy and paste code from text editor to terminal, enabling a nice, tight feedback loop. I first learned about REPL-driven development from a Clojure guy, and he made it sound like an amazing way to work, so I wanted to try it. But in my work, I use primarily JavaScript. Most of my code base is JavaScript. Changing languages to Clojure was not an option. Now I recalled that semantically, JavaScript is very similar to Scheme, and Scheme is a Lisp, so theoretically, REPL-driven development should have worked just fine in JavaScript. But when I went out looking for the tooling, I found that it just wasn't there yet. I'll come back to why that is in a bit, but suffice to say that I had to roll my own REPL. Now you might be thinking, don't we already have state-of-the-art live programming tools in JavaScript? For example, we have live reload, hot module replacement, and storybook in the browser. We have test watches on the back end, and we have web-based playgrounds that update as you type. And one problem with these is that they lock you into a coarse-grained execution model. Even if you just want to run a little bit of code, you're forced to run at best the entire module and at worst the entire application. And this is a problem because it gives bugs so many places to hide. Another problem is a certain lack of generality. Why do we have a different set of tools when we're working on the front end as the back end? And as we'll see, REPL-driven development can satisfy both of these cases with the same mechanism. The tool, which I called Replete, ended up as an editor-agnostic REPL that supports evaluating the entire JavaScript language on several platforms, including Dino, Node.js, and browsers. I'll give you a demo. To start Replete, I press Ctrl-R. The editor plugin responds by spawning the Replete process, which speaks JSON over standard I/O. The simplicity of this interface lets Replete integrate with a wide variety of editors. A new panel opens to hold Replete's output. Code is evaluated by selecting it and using a key binding, for example, Ctrl-D for Dino. If no code selected, the current line's evaluated. The resulting value gets printed to the output. If there's an exception during evaluation, that gets printed instead. If evaluation locks up the main thread, nothing gets printed and you'll have to restart Replete. Let's fetch some geospatial data from an API. The response looks okay. We'll read the body as JSON. Now that's a lot of text. Some kind of object inspector would be useful here. But what we can do is visualize the data on an interactive map. But this means evaluating code in a browser. Let's try that with Ctrl-B. Now evaluation fails because we're not connected to any browsers yet. Remember that link that was printed when Replete was first started? We'll open it up in Firefox. Here in the DevTools, you can see this WEBL talking to Replete over WebSockets. Essentially, the WEBL is a blank canvas on which we evaluate code, but it's also a dev server that can serve static files such as images and CSS. Now we're connected, let's take a quick detour. One challenge I faced was that JavaScript semantics are no longer REPL friendly as of ES6. For example, it's illegal to redeclare variables. Replete permits redeclaration by applying a source transformation. Notice how this top-level code has had its let keywords removed. Moving up the stack, we see that this code is evaluated inside a with block with an artificial scope object populated with the top-level declarations. This approach prevents you assigning to an undeclared variable or accidentally polluting the global object. Back to our example. Let's prepare an element to hold our map. We'll import a library to render the map. But this fails because Leaflet resolves to a CommonJS bundle due to its faulty package manifest. Browsers don't support CommonJS, and so the file is interpreted as a module with no imports. Fortunately, Leaflet also ships as a module. Let's take another detour to discuss modules. Notice how the import statements have been removed entirely. This is because eval chokes on import statements for two reasons. One is that eval is synchronous, but importation is asynchronous. The other is that imports may be specified relative to the current module, but eval takes only one argument. This explains why import statements are supported by very few JavaScript REPLs. Moving up the stack, we find the imported value is extracted from an imports array. Moving up once more, we find an array of dynamic imports doing the actual work and producing the imports array. The imported URL contains a version number that increments whenever the module or one of its descendants changes on disk, allowing us to bypass the runtime's module cache. Our map looks all screwed up because Leaflet depends on an external CSS file. Some frameworks allow for the injection of CSS via JavaScript imports, but browsers don't support this and nor does Replete. Rather, the import.meta.resolve function is used to resolve a URL to the CSS file, which is then loaded via a link element. The same function can be used to resolve other static files, such as images, and it has the benefit that paths can be specified relative to the current module. Even though we declared the GeoJSON variable in the Dino REPL, we haven't declared it yet in the browser REPL, so we get an exception. One tricky aspect of using the REPL like this is that just because code is visible doesn't mean it's been evaluated. And inevitably, it becomes too difficult to keep track of which code has been evaluated when. And that's when we start evaluating the whole module. But when we do that, we find we have two containers. To clear out lingering elements, we reset the DOM. And there's our data. There are a couple more caveats to keep in mind when using Replete for front-end. One has to do with entry points. Conventionally, we try to put as much content as possible into the HTML served to the browser, and then sprinkle on a bit of JavaScript to bring the DOM to life. Replete, however, assumes a JavaScript-first approach where the DOM is never pre-populated by HTML. This means Replete is more useful for developing behavior-driven web apps than content-driven web sites. Another caveat is that Replete doesn't tend to support front-end frameworks out of the box. Many frameworks come with a dev server that handles transpilation of their DSL, but since Replete takes the place of this dev server, it must be configured to perform the desired transpilation instead. This can be a source of friction when attempting to incorporate Replete into an existing code base. 4 years of using Replete in a commercial codebase has taught me a lot. One inescapable practice that emerged was writing demos into the source of modules. Such modules can be exercised by simply evaluating the whole file. Of course, we don't want that demo running when the module is just imported, so we wrap it in a conditional. When import.meta.main is evaluated by Replete, it's always true. The only other time it's true is when the module is run as the entry point of a command line runtime. When your modules are able to demonstrate themselves, it becomes convenient to navigate the dynamic behavior of your application via the code. Furthermore, a module's ability to run itself in isolation implies good modularity, making implicit dependencies like CSS resets and centralized state management much less attractive. All in all, REPL-driven development in JavaScript looks and feels radically different to conventional JavaScript development. It penalizes sophisticated source transforms, discourages the use of HTML, and demands a high degree of modularity. What it provides, though, is a fine-grained understanding of code's behavior, from expressions up to modules, out of which can be crafted applications that are reliable and maintainable.